Section 4.4.
Graphing sine and cosine functions without a calculator.
Exactly, because you don't need a calculator for this.
We don't need no stinking calculators.
Because we're going to teach you how to do it. We're going to teach you right now. So,
By hand.
Yeah, by hand. So whenever we have like sine of x here, there's something that happens every time that we graph sine of x. If all it is sine of x. And that is that, okay, it's in red. You can't tell that on your notes. There's not two colors on your notes, but you could color it now. Like you could go ahead and color this red one right here so that you can tell the difference.
Color it with a highlighter. Might
exactly,
be easier to see,
a highlighter or a different color pen.
Yeah, use a crayon or something.
Yeah, and so sine of x always starts here at 0, 0.
Right, every time?
Every single time. And then it always does one of these little curve things.
It's got like a hump,
by 2 pi.
A hump and a valley.
Yes, a hill and a valley by 2 pi. Okay, and we're going to talk about some of this here in a little bit, but that always happens. It starts at 0 and it goes up. It comes back down and the hill ends at pi. Then we've got our valley until we get to 2 pi. It goes up to 1 normally and it goes down to -1 normally. And it just keeps going back and forth between those.
Because it's periodic.
Yes, and that's what we mean by periodic, is that these values like 0, 0, pi 0, 2 pi 0, those values keep happening over and over and over again that we get that 0. It's repeating itself.
So if you're just looking at the parent function of sine, this is the shape that you're going to have.
Right, and then everything else that we look at when we graph sine functions is some kind of a transformation.
Right, and it
just
follows.
Just like what we...
Yes.
Go for it.
You too.
Just like what we've talked about the entire year.
Vertical stretch, horizontal stretches, movement left and right, movement up and down, all those same exact rules apply.
In the exact same kind of way, just we start off with this as our parent function. So example 1, analyze the graph of sine x.
Let's do it.
Okay, so how about domain?
Domain is all real numbers because every value of x we can plug into that puppy.
Yeah, you can plug in anything for x and get some value for y. So all real numbers, which is negative infinity to positive infinity. How about the range?
The range would be, bye Gabe.
See ya, thank you.
The range would be from -1 to 1 because we don't have any y values outside of that particular
range of
range
values.
Of values.
Like we're never going to end up down here at -2.
Not with this base parent
ever,
function.
ever.
Right.
So that means that our range is from -1 to 1. Now, does that include -1?
It does, because if you were to take the sine of
something
of, let's go like 3 pi over 2 maybe.
Yep, sine of 3 pi over 2.
It's going to be -1.
It is.
It's not going to be close to -1. It is going to be -1.
Right. So it's kind of like with a parabola, how this would be kind of like a vertex of a parabola. It's similar to that. It actually really does touch -1, and it really does touch +1. Domain range. How about, is this a continuous function?
It is continuous. At no point in time will we ever pick up our pencil or pen, if you're one of those people, while we're drawing out the graph.
So we would say this is continuous.
Definitely continuous. No asymptotes here.
Okay, increasing, decreasing, or constant.
Oh my gosh.
This is the one that's a little unpleasant.
This is a little tough.
Because check it out. I would say that our graph increases from here until here.
Right.
And like this part of our graph, right here. And then it increases from here to here in the same sort of way, like our graph keeps repeating. But that's not the only place. Like, just in the part that we have drawn, we have 3 different places.
Right.
But
there's a pattern.
Okay, let's figure out that pattern then, right? So let's figure out what these points are, because we have 0, we got -pi, -2 pi. So in between here, in between -2 pi and -3 pi is -5/2 pi.
What if we did something a little closer to the origin? I think it might be easier.
Oh, okay, fine. So between 0 and -pi is -pi over 2.
Right.
Okay, and then between 0 and pi is +pi over 2. So we could say that it's increasing from -pi over 2 to pi over 2. And you can use brackets or parentheses on increasing in this case. Okay,
but not only that, it does it again a little bit further up the road.
Okay, so between pi and 2 pi is 1.5 pi, which is 3
pi over 2.
And then between 2 pi and 3 pi is 2.5 pi, which is 5 pi over 2.
Right. So then it increases from 3 pi over 2 to 5 pi over 2, but we don't have time to write down the infinite number of places that this graph increases.
No, we don't.
Mrs. Stevenson and I, we like math a lot, but we don't want to write down all of the infinite number of times
we don't. We don't at all. So what we would do for increasing is we would say, well, if you take negative pi over 2 and you add, how far apart is the starting values? Pi over 2 and 3 pi over 2.
Is that a pi? I believe that's a pi.
Those are pi apart because what we can do is we can subtract them. 3 pi over 2 minus a negative pi over 2. Oh wait, that's really like we're adding, ching ching, wall ball bing bang. So that's pi. They're pi apart. So what we can do is we can say, well, if I add pi to this, I get another interval. If I add pi again, that's another interval.
So it'd be like k pi, where k could be any integer.
Okay. And then the same thing with pi over 2, because pi over 2 and 5 pi over 2, those are also pi apart, so we can add k pi. And then we would at some point need to say like where k is
any integer.
Any integer.
Any integer. Not a fraction, not a decimal, but an actual integer like 3 or negative
because we're
2.
saying if you wanted to find like 5 intervals where it's increasing, just start plugging in numbers for k, like 1, 2, 3, 4, and you would get in those different intervals. Decreasing is going to work kind of the same way, right? Except that instead of the values we have, it's the other values. Like it's decreasing here from pi over 2 to 3 pi over 2.
Right.
So what we have to do in either case is we have to pick an interval to start off with. So on the first one we picked negative pi over 2 and positive pi over 2. Here I'm going to pick positive pi over 2 and positive 3 pi over 2. And then we add k pi.
Right.
On both of them.
So there's your decreasing. Increasing and decreasing. And they should be on in-between intervals. Like they shouldn't match at all.
Yes. So that's increasing and decreasing. How about symmetry?
This guy actually has symmetry with, wouldn't we say the origin maybe? Odd? It's an odd function.
It's an odd function. It has symmetry about the origin because if we take this part right here, for example, from 0 to 2 pi, and we rotate it around, we get this right here.
Shut the front door. So you could graph this on your calculator, turn your calculator upside down, and be the exact same graph.
Right. Incidentally, I know we said we weren't using our calculator, but if you were to graph this on the calculator, what mode would you need to be in?
Well, you could graph it actually in radian or degree mode. However, the way that your calculator is defaulted when you graph it, you want to be in radian mode to get the true picture. If you just are in love with degrees and you want to graph it in degree mode, you have to change the window settings to go from 0 to 360.
Well, that sounds like a lot of work.
That's a few more button punches.
So what if we just always put it in
just
radian mode?
If you leave it in radian mode, you'll be great. Now, if you're graphing on your calculator and you see a straight line and you're like, there should be some curves here, you're in the wrong mode. You need to go from degree to radian.
Yeah. How about extrema?
Oh boy, there's an extrema every pi units.
Every pi units, because there's one right here. There's a max right here at
pi over 2.
Yeah, pi over 2 comma 1.
1, yeah.
And then there's another one here at 5 pi over 2 comma, oh, it's 1 again.
Hey, guess what? There's going to be another one 2 pi units later, because that's how long it takes to get back to positive 1.
Right. Every 2 pi, we've got a maximum, and then every 2 pi, we've got a minimum as well. These are 2 pi apart.
So here comes 2k pi.
Right. So pi over 2 plus 2k pi. But the 1 just stays like
it's always
every
1.
single time that was 1.
Never goes past 1.
Okay, where k is any integer. Our minimums then start like we can use this one, 3 pi over 2.
Yeah, 3 pi over 2. Yep.
And
plus 2k pi.
Yeah, I meant a plus, not a comma.
That's okay. Plus 2k pi. There you go. Good job. Good job.
And then it happens for our y value at
-1 every time. Period. End of story. Double stamp C's.
Got it. What else do we need to do here?
No asymptotes.
No asymptotes.
There's
now,
really no end behavior here because the end behavior doesn't necessarily approach anything in particular.
Before we go there, there's no asymptotes, but this is bounded above and below.
It is bounded above and below.
And that's because we don't ever get to positive infinity or negative infinity for our y values.
Right.
So we could just say it's bounded, or we could say bounded above and below. Okay, back to what you were saying about end behavior.
The end behavior, if you'll notice on this, the sine function and the cosine function for that matter, because the cosine will be very similar to this, they bounce back and forth between 1 and -1. So if we were to look at the end behavior, we don't necessarily have specifically defined behavior as x goes to infinity.
Because it just keeps going back up and back down.
Yeah, the thing
never
never sits
start
still.
getting closer and closer to some value. So would we say that this limit is undefined?
I would say that that's fair to say, or does not exist maybe. Hello, Mr. Allstat.
And same with the limit as x approaches
Positive infinity.
positive infinity of f of x.
The limit does not exist. I hear that's in a movie.
Mean Girls? Or some other movie.
I think Mean Girls, right?
Yeah, I don't know. I haven't watched it recently enough to know. Yeah. So that's sine, and then here in a second we'll bust out cosine as well. But I think I'm gonna have to get rid of. I'm gonna need to get some room. I have to clear this.
We'll make room. We'll do cosine.
Yeah. Now let's do cosine. Cosine is the one in green. And
which is not the one in red.
Yeah, and it just varies just a little bit on a few things. If you were to want to draw y equals cosine x, like if that's something you wanted to do, then you would have to start at 0, 1, and then you draw your graph going down. Okay, and so instead of us being 0 at 0, pi, and 2 pi, we end up being 0 at pi over 2, 3 pi over 2, and so on. And basically, by the time we get to 2 pi, we need to be back up here. Okay, because this is a periodic function that every 2 pi, the same thing should be happening. So if we start here at the top here, then 2 pi later, we should be back at the top.
Right back where we started.
Right back there, yeah. Okay, so we want to analyze this. So domain, for instance, right here, domain.
That would be all the x values that you could put into the function, and we can put every x value into this function. So the domain goes from negative infinity to infinity.
That didn't change from what it was with sine. Our range doesn't really change either. Even though we're getting to 1 and -1 at different spots, that's still the values of y that we're oscillating between.
That we're going between, which is -1 and 1. I feel like your 2 dots there are not very good.
Thank you. Thanks. I'm not. If I try to fix it, I'm just going to screw other stuff up. So I'm just going to leave it.
Okay. All right.
This is also a continuous function.
It is.
So that's similar.
We don't ever pick our pencil up when drawing sine and cosine. Those are the only 2 trig functions, though, where you don't pick your pencil up while drawing. All the other ones are going to have continuity
tangent
issues.
And stuff. Let's not spoil 4.5 for them.
Sorry.
Increasing, decreasing. Remember, this is the one that required some work. And should we say that we did?
Yeah, we had a slight error, not major.
That we figured out.
And we caught it in between recordings.
Yeah, so we made a note of it earlier in the video, assuming that the editing that was supposed to happen happened, which of course it did. But we're going from negative pi to 0, for example, here. But then the next place that we're increasing happens 2 pi later, and we said it was happening just 1 pi later. But if from this value to this value, from negative pi to pi, there's 2 pi's.
You might draw a bracket in a different color to show.
Draw a bracket around.
Like make a little, and then
like from
right there to right there.
How far apart are these? Those are 2 pi
That's
apart.
2 pi apart.
Right. So our increasing intervals, and you find one of them, any one of them.
Doesn't matter which one you pick.
Doesn't matter which one. So I just found, for example, negative pi comma 0. Oh, but I need to put
plus 2k pi.
2k pi. And then 0 plus 2k pi, or you could just put 2k pi there if you wanted to. But it's increasing for any integer that you put in for k.
It increases.
It is increasing in those intervals.
Right. And that's a really, this whole situation with the 2k pi is really challenging one to try and understand. So if at first you're not getting it, when we ask for increasing and decreasing behavior, write it down because we said so.
Right.
And then as you start doing that, the understanding will take place.
It should, definitely.
But don't stress out if you don't get it all right away.
Right.
Okay, this is going to take some practice.
Right. So now we're decreasing from 0 to pi, as that's just one interval where we're decreasing, but it's going to happen again every 2 pi. So we can say from 0 plus 2k pi, comma, pi plus 2k pi. All right, that's increasing and decreasing symmetry.
This one, if you were to fold the graph in half, right over the y-axis, they're going to mirror each other.
Hamburger style? Hot dog style?
Whichever style it needs to be, it's going to be...
It folds in half, and that's called symmetry on the...
Y-axis symmetry, because this function is even. Yes. Even, boys and girls.
Symmetry about the y-axis. And those two things, the fact that sine is odd and cosine is even, that can really make a difference in calculus. That can really make a difference.
It does get quite important.
Yeah, I can't tell you how many times I've had to deal with that in my life. There's been a lot. Anyway, what's after symmetry?
There are no asymptotes,
No
with this bad boy.
Okay.
No asymptotes at all. What about in behavior maybe? In behavior is not happening because just like with the sine function, as you go towards negative infinity, your y values change all the time. And they change between -1 and 1. So we don't approach a specific number or negative infinity or positive infinity.
Right.
And everything I just said is repeated again as x goes to positive infinity. Just you don't have that in behavior.
Right, because we're oscillating back and forth.
But it is bounded though. It's bounded above and below, so it's bounded because there are values that we just don't ever go to for y. We never go past 1 from the parent function.
Right. Maximums and minimums. We've got a maximum here at 0. There's a maximum. We've got another maximum at 2 pi. So there's a clear way to see, okay, those are happening 2 pi apart because one's happening at 0, one's happening at 2 pi.
That's got to be a distance of 2 pi then.
So our maximum is, we have the point 0, 1, but not just 0, 1. We've got
0 plus 2k pi. The maximums are going to be the same thing except this time, or your minimums. Your minimums are going to be the same. They're going to be -1, just like with sine, except now your minimums are going to occur at pi.
Right down here at pi.
Plus 2k pi. Yeah, there's your minimums.
1, 2, 3, 4, 5, 6, 7, 8, 9. That's everything. So that's cosine. So now let's look at the transformations. Is what's coming next. Like, how do we know what's going on as far as like when we throw other numbers in there?
What's it do?
Y equals sine x and y equals cosine x. Those are great functions,
right,
but they're not the only things that we could have.
By the way, there's a lot of similarity between these two. So if you can just get where you're really, really understanding one, you should be able to analyze both.
Yeah, because the other one is just a little bit over.
Mm-hmm.
Okay, so. Hello there. We've got some information for you about a thing called sinusoids.
I like that. Sinusoid?
Sinusoid.
It's fun.
A function is a sinusoid if it can be written in the form f of x equals a sine of bx plus c plus d.
Right.
So definitely anything that has, or anything at least for now, that has a sine in it is a sinusoid.
Or cosine.
Well, that's what I was about to say.
Oh.
And we'll look at this a little later, but cosine and sine are so related that really cosine is just like a shift over of sine.
Or vice versa.
Or vice
but
versa.
We typically refer to it as a shift of sine.
We do. We're a little biased that way, I guess.
Yeah.
But there's some things that happen with these different letters. We've got here A, B, C, and D. Like each of those has to do with a certain type of shift or stretch or shrink.
Hey, just like they were with all the other functions we've talked about to this point in time, the exact same,
the exact same
shifting,
kind of thing.
shrinking, moving happens.
So the first thing, and probably actually one of the easiest things I think with sine and cosine functions, is the amplitude of the sinusoid.
Now here's the deal. We're going to give you a test later, and we're going to ask you for the amplitude on every single question that we put on that test. But there are only two functions that have amplitude, and only two, sine and cosine.
Technically, yeah. Only two that actually have a legitimate amplitude.
Amplitude. Amplitude is the key word here.
Amplitude is talking about how much does our graph go up and down.
Right.
From the main point. It's like sine and cosine every single time. There's like this line that they are oscillating around, right? And so in normal y equals sine x, this line that they were oscillating around was the x-axis. But that'll end up changing at some point. So amplitude is this line right here. How far are we going up, or how far are we going down? Because those should be the same. We should always go up and down the same amount.
Right.
And so if we're looking at our function here, this sine function, it turns out the absolute value of whatever a is going to give us the amplitude.
Every time.
Every single time. So for example, if we have like y equals 2 sine x, okay, that 2 that's in front, whatever number is right in front of sine,
is amplitude.
They're being multiplied together, that's amplitude.
Right.
And so when we draw this, then like instead of us going up to just 1 and down to -1, we would go up to 2 and down to -2. So that is our vertical stretch, just like when we did other
Wow, look at the
things.
green guy in there. There's a vertical stretch going on in that situation.
Do you happen to remember? I think the red function here is y equals
looks like
sine
x.
And so, yes, what's going on here with this green function is our amplitude has been changed. And so this green function, it looks to me, since we still have one sine curve, one hill and one valley by 2 pi. So all that's changing is that this has an amplitude of this value up here, which is...
I believe it's 3.
That's 3. So this green function is the graph y equals 3 sine x.
Now how hard was that?
It wasn't that bad,
No,
to be
it wasn't
honest.
bad.
No. Okay, so now the period of the sinusoid. We've talked about that sine and cosine are periodic functions.
Right.
And so the period of it is talking about how often it repeats. And we've already kind of mentioned this quite a bit so far, this particular section, that every 2 pi things are repeating. Right?
Right on schedule.
Right.
Every 2 pi.
We start here at 0 and we have one hill and one valley by 2 pi, and then it starts over and we have another hill and another valley.
So that's what you're looking for periodicity.
Periodicity, yeah, exactly.
With sine and cosine is when do you go all the way up, when do you go all the way back down, and when do you start repeating the same pattern of values. Not a specific value, but the same pattern of values.
Right. So every 2 pi. And so what happens is that they can change that on us. They can mess with the period. They can, like, look at this purple graph. This definitely goes up and then back. It has a hill and a valley way before 2 pi happens. It happens like right here at like pi over 2. It's had its whole sine curve, one sine curve by pi over 2. So what you do is whatever number's in front of x here, you do 2 pi over that, which is written right there.
Right.
2 pi over that number.
Okay, so when you're talking about period, then just whatever that number in front of the...
Right in front of x.
Right in front of x.
You do 2 pi divided by that, and
it'll
gives
tell
you the period.
Yes, because sometimes it takes more or less time.
Right. And yes, and the reason we use 2 pi is because that's the normal period, and so what's happening here is we've got a horizontal shrink or stretch.
Right.
Because we're either accordioning out or accordioning in.
Yep.
We've got a horizontal stretch or shrink. This is really the main time that we see legit horizontal stretches and shrinks happening.
Right.
Every
with
other
the sine
time
and cosine
it's normally
functions.
vertical or
right.
whatever. But we can stretch horizontally or shrink as well as vertically at the same time with these guys, and they're doing two completely different things.
Because if we were to look at a vertical or horizontal shrink with like something x squared,
yeah, we could talk about
you could talk about it, but you could also do it vertically. And,
yeah.
And with the sine and cosine functions, it is obvious what's going on.
It's completely different.
Yes.
Completely different situation between those two. So frequency of the sinusoid.
That's going to be like how many times it happens.
Yeah, how many sine curves do we get by 2 pi?
Yeah.
Right? And so instead of doing 2 pi over b, we do b over 2 pi. And the same thing with if it was cosine, either one of those. And the period and amplitude also would apply to cosine. Oh, wait, it says that on those. Never mind, it said that. But, so like if we
So if you look at the purple graph,
oh yeah, purple graph.
Frequency of this guy, if you start at 0 and go out to 2 pi, so there's 0 and there's 2 pi. Look how many bouncing up and downs we got going on.
There's 1, there's 2, there's 3, there's 4. So we get 4 sine curves by the time we get to 2 pi, which means that we have 4 over 2 pi. No, that's not it, because we don't have b. We don't have the function.
Oh,
b over 2 pi equals 4.
Yeah.
And then we could find b if we wanted to.
Right, if we wanted to, yeah.
Okay,
so there you go.
Let's move on to something else. Example 3, find the vertical stretch or shrink, which is the amplitude.
Sorry, I'll own up. That's my whoops. We're finding amplitude here.
Okay, so the amplitude, if we remember back from the previous slide, is the number that's in front of sine or cosine.
Right in front of sine or cosine.
Okay, so what is the number right in front of cosine?
Well, how many cosines are there?
I have 1 cosine.
That's what I see, so that means there's a 1 in front.
So there's not a vertical stretch or shrink.
There's not, but the amplitude is 1. So I guess you could say it's being stretched by 1, but I don't know.
Or shrunk by 1.
Or shrunk by 1.
We should just say the amplitude.
No, it's an amplitude 1. Yeah, it's good safe.
Okay, b, what's the number in front of the cosine?
Okay, that's a half. So amplitude in this case would be a half. Now this would technically be a shrink because our normal parent graph goes all the way up to 1. So if we don't go all the way up to where we originally start, we're going to have some shrinkage.
Right, so vertical shrink of 1/2.
1/2 a Ruskies.
All right, now this is kind of hard to read on here at least. That says -3.
-3 cos x.
Now, when we do this,
cos x.
The number in
Grandma fell and broke her cos x.
The number in front of cosine, we take the absolute value of whatever that is.
Right.
So this is a +3. It doesn't stretch. It doesn't stretch by a -3.
Stretches by 3, and this is.
Go ahead.
This is an instance where amplitude is always positive.
Right.
Always.
Because it goes up and down 3. We're talking about a distance here. How high does it go? How low does it go?
Right.
Like amplitude is 3. Never mind. Vertical stretch of 3.
Right. Now, the negative in front means it reflects over the x-axis.
Right. It reflects over the x-axis.
I'm just taking in, making me think about Christmas break.
Okay.
Yeah.
Enjoy it.
Now, these two things on example 4, find the horizontal stretch or shrink in period. Those actually are kind of
No, that's going to happen. And so, again, we've got our parent function to start with. So there really is nothing going on in that.
Right. There's no horizontal.
Right. He's just normal. As normal as one can be.
When talking about trig. Okay, but the period of this is 2 pi over the number in front of x, which is 1.
Right.
So 2 pi over 1.
Which is 2 pi.
So the period is 2 pi. Because again, that's our parent graph. That's what's normally going on. Now on this one, -2 sine of x over 3. Well, we've got a 1/3 in front of x. And so when we talk about horizontal stretches and shrinks, if this is a fraction, that means we're stretching.
Right, it's the reciprocal.
Yeah. So this is a horizontal stretch
by 3.
By 3. Okay, the period is 2 pi over 1/3.
Right, which now rewind back to like 5th grade or whatever. When you divide by a fraction, you have to multiply by its reciprocal.
So this is 6 pi.
So it's going to take 6 pi units to completely go through one whole
shebang,
rinse and repeat sort of thing.
The period of it's 6 pi. And so if you need to look at the period first and figure that computation out, 6 pi, doesn't it make sense that it horizontally stretches because 6 pi is longer than 2 pi?
Right.
So.
What do you think, Mr. Boulware?
Yes, horizontally stretch.
Yeah, totally. Okay,
Or
so
vertically shrink.
Jeez.
okay, so now y equals 3 sine of negative 2x.
Wow.
So that negative inside,
Doesn't matter for shrink or stretch. It
Right.
only means that now we're going to reflect over the y-axis.
right? This is making our x negative, which means we are reflecting across the y-axis.
Right.
Okay, but it didn't really ask us about that. We're just
No.
pointing it out. What it did ask us though is
Horizontal shrink or stretch.
so since we've got a 2 here, that means that we're shrinking by a factor of 1/2
Right.
horizontally.
Right, because it's the reciprocal of when the number is outside of the function.
Horizontal shrink of 1/2. And then our period is 2 pi over 2.
Over 2, not -2, but
Nope.
just 2.
Which is pi. So the period of the function is pi.
And that tells us then how far we have to go before everything starts to repeat.
Right.
Not just one specific value, but all the values, the
One
pattern
hill,
of values.
one valley has to happen by the time that we get to pi.
Right.
So
you can tell then, accordion in.
yep, it's going in. All right, example 5. Find the frequency of f of x equals 4 sine of 2/3 x and explain what is happening graphically. So we said frequency on the previous slide was the absolute value of b over 2 pi. I think at least not on the previous slide, a couple slides ago. And so b is this number in front of x, so it's 2/3 on top. Since it's already positive, that absolute value keeps it positive, over 2 pi. And so to actually work this out, we would have 2/3 times, this is like 2 pi over 1, so we flip up our fraction and make it 1 over 2 pi. Our 2's cancel out, leaving us with 1 over 3 pi. So that means, if we explain what is happening graphically, well, this, because it's 2/3 and it's on the inside right in front of x, that's a horizontal stretch of the reciprocal, which is 3/2. And so what's happening is that we'll have one sine curve at 1 over 3 pi. All right, Hazelwood's over here with us now, and we were talking about the frequency of this was 1 over 3 pi, and that's the reciprocal of the period.
Right.
We're saying that this is going to complete one sine curve by 3 pi. That's what this means. So graphically, we've got a horizontal stretch of 3/2, because normally it completes by 2 pi.
Right.
3/2 of 2 pi is 3 pi.
Yeah, and you can look at this on your graphing calculator too. Like this is kind of a, frequency can be a little bit of a tricky monkey to try and,
Wrap your head around?
yeah. And so if you
Why
will,
would you wrap your head around a monkey?
really awkward. So what you can do though is put this on your calculator and just look at your calculator, tell the x coordinate to be 3 pi, and see where it goes on your graph, and it should line up to show you that it's a completion.
It should indeed. You want to talk about how to graph this?
You know, great idea.
Okay, so what's happening here, the way we graph a sine is we need to look at two things. We've got this amplitude of 4, which means that our sine curve is going to go as high as 4 and as low as -4.
Every time, period, without fail.
Okay. 2/3 here, we just said that the frequency is 1 over 3 pi, or the period is 3 pi, okay, which is important. So if we hadn't been asked the frequency, we would have done 2 pi over 2/3 to find that that's
Right.
3 pi. And so what I normally do is I normally make like a, let's make this 3 pi out here, and let's make this -3 pi. And the way I like to do it is divide it up into fourths. Is that how you roll?
Yeah, wow, I roll the exact same way.
Halfway between 0 and 3 pi is 3/2 pi.
Oof, 3/2 pi. I know it's a fraction, but it works out perfect. That's the beauty. That's why dividing into 4 is so amazing.
And then, should we find those tick marks, or are we just fine with having those tick marks?
You know, I'm fine with having them, but if you took half of 3
pi over 2?
3 pi over 4.
3 pi over 4. Okay, we don't necessarily have to label all of them, though. Just if we divide into fourths, we have to remember that sine starts at 0. And if it's a positive sign, which
it's going to go up to 1.
It goes up first.
But in this case, 4.
Right. In this case, 4. So what happens is we have to be back here at 3 pi. Halfway will be at 0. And so we've got a hill. And then we've got a valley. Which that last valley there looks a little awkward, but hopefully you guys
it's all good in the neighborhood.
And then just go backwards here. Okay, but what was important is really labeling it was important.
Right.
We had to go up to 4 and down to -4. We have to have one sine curve, which means one hill and one valley by 3 pi. And that's it. That's how you graph a sine curve. If it was cosine, we start at +1 if it's positive.
Right.
Start at -1 or -4 if it's negative.
You got it.
So
just use your general. Hey, you can use one of these bad boys too while you're learning.
Yeah.
Always helpful.
Yeah, to make the connection there. But the thing with the calculators, it's not going to tell you these in pies. You're going to have to figure those out yourself. For 3 pi, it's going to have 9 points something.
It'll be some really weird deal. So you do have to have some patience. But it is possible to to graph by hand fairly easily and then double check on your calculator.
Right. You ready to do example 6?
Yeah, let's rock it.
Right, the cosine function as a phase shift of the sine function.
Ooh, a phase shift, like Star Trek.
Phase shift is a fancy word for a horizontal shift. Right?
I like Star Trek better.
Okay, well, it has nothing to do with Star Trek.
But it sounds cool.
Okay.
Phase shift.
A normal sine curve.
They line up like this.
Normal sine curve.
Here's the sine curve, here's the cosine curve. Notice how my hands are not quite identical, but they are the same. And phase shift, we're going to take what's different and line them up so that they're identical, that you can't tell the difference. Look, she's drawing it out right now, way better than my hands will ever go.
This one is cosine because it starts up at 1. The other one was sine. And so we're trying to write the cosine function as a phase shift of the sine function. So we're trying to do y equals sine of something. Okay, since we're talking about a phase shift, which is a horizontal shift, it's going to either be adding or subtracting something.
It's exactly like what you did with all the previous functions that you've worked out where we've had to move left and right. It's the exact same thing.
Exactly. So what we're doing is cosine, which is what we're trying to write as sine. All of these points are what? This is pi over 2. There's a difference of pi over 2.
Difference of pi over 2.
And really we can make it either negative or positive because either we can say, oh, well, it's going this way, or it's actually, is it going backwards? No, going backwards is not the same, but not pi over 2.
Right, not pi over 2, but it would be more.
Moving right pi over 2, which means minus pi over 2.
There you go. That's it. That's all there is to it.
And that's what it's asking.
You got
us. It. Example 7.
We're going to find the equation of a sinusoid. Remember, that's a sine curve. With the period of pi over 5, an amplitude of 6, and it goes to the point 2, 0.
Okay, so let's think about what we know. We know that amplitude is 6. That's our A.
That is...
Okay. And then we know it's a period of pi over 5. To find the period, we normally do 2 pi over B. We're saying that is pi over 5.
You have to know, just go with, what is your period? 2 pi over B.
Yep.
What does it equal pi over 5?
Okay, and then let's solve this. Do a little cross multiplication action. 2 pi times 5 is 10 pi.
By the way, we can do cross multiplication because there's an equal sign in the way, not because that's the rule of multiplying fractions.
Right. We're trying to solve for something. We've got a fraction on both sides. So to get B by itself, let's divide pi on both sides.
Divide by pi!
I could use some division by pi myself. I don't know what that means. B is 10. Okay, so that's another
part. We've got
part.
A and B. Bingo, bango.
The other thing, and we really haven't talked about the whole vertical shift thing. I feel like...
Well, here's how vertical shift is going to go. Remember way back when we looked at stuff that was like all the different functions that moved around a little bit?
I remember.
Up and down, perhaps. Remember, all the up and down stuff took place outside the parentheses. So if we're going to move up and down, it's going to be right there, right there at the plus D or minus D part, as it were. Remember, if you're outside the parentheses, you do exactly what the equation says to do. If you're inside the parentheses, we're part of the super secret opposite society. And that doesn't change. That does not change for trig functions.
Right. It's all the same. So if we've got like a +3 out here, that means our graph is shifted up 3. And so then what it does for sine and cosine curves is it makes that be the place where we're oscillating around.
Right. Right.
So that instead of like normal x-axis, we're oscillating like...
We're going to actually
If we're shifting
go
up 3, then we're going to go up here to 3, and that's where we're going to start oscillating.
I like the way you think.
Okay.
Okay.
So the reason we're bringing that up, we've got the A, we've got the B. I don't think we're going to have a C here. I don't think we have a phase shift.
I feel like what you're saying is correct.
But this 0.20, I think, might be telling us about a vertical shift. So I feel like I need to draw out what's going on and think about this, because we've got an amplitude of 6, the 0.2, 0. Oh, maybe I'm wrong. Maybe this is a phase shift.
Oh, no.
Because 20 is right here. So it could be that we've got this action going on. Like that's where our sine curve starts.
You know, maybe.
And that right there is a phase shift. It's not a shift up and down. It's a phase shift that we are moving to the right to.
No problem, though. It's not a problem.
We can do that.
We can still do that. We can totally do that. In fact, it's even easier now to do that. You know, it doesn't matter. It doesn't matter. They're both easy. They're both easy.
All right, so A is 6. B is 10.
Right.
But I feel like there's some issue that happens. Is there some issue that happens when we've got a phase shift and a number in front? Are we gonna subtract 2 here?
I believe so.
Okay, and then there's not a vertical shift.
Then there's not a vertical shift.
Okay, but okay. Here's what happens: is we put this in parentheses.
Yeah.
Okay.
There you go. There you go. Because we want to actually. To the x, we want to move 2.
Right.
But also to the x, we're going to multiply by 10. So we've got to look at those individually.
Yeah. So y equals 6 sine, and then if we distribute, that's 10x minus 20.
Yeah.
And so when we have a phase shift and we have a horizontal stretch or shrink, which is what's going on here, there is a little bit of an issue there that's kind of hard to wrap our heads around. I feel like. Right. So when you write this, stick it in parentheses and then distribute.
Practice it and graph it. Graph what you, hey, it's okay. Graph what you get and just double check. Does it go through the point that you're given? And you can look at a table of points to figure that out. Or you can go to your calculator and say x equals 2. What is y?
Yes.
It needs to be 0.
Yeah, it does.
And if it isn't, then you've got a whoops.
Yeah.
And just do a real quick check in here. 10 times 2
is 20.
Minus 20 is 0. The sign of 0 is 0. So we're good.
Awesome.
There's all kinds of ways to check.
We checked it.
Yeah.
It works. All right.
You know why it worked?
Because we did math. Because the stud monkey and super monkey here, that, are you thinking code word?
It's possible that might.
Code word monkey? Yeah. Code word monkey?
Code word stud monkey.
Stud monkey?
Yeah.
Okay. Code word stud monkey.
There you go.
So, and we said it out loud. So all you people who keep claiming that you're writing stuff down and don't see the code word, we just said it.
Claiming.
Find the equation on example 8 of a sinusoid that goes from a minimum value of y equals 5 at x equals 0 to a maximum value of y equals 25 at x equals 32.
I don't understand.
Should I draw a picture? Like, do you literally not understand, or are you being theatric? Y equals 5, x equals 0, so...
I'm never theatrical.
Whatever. Theatricosity. We've got this point 0, 5 that we know about, and we've got this point over here at x equals 32, y equals 25. Well, my scale's a little off here.
Wow, just a skosh. But that's okay. Go ahead and draw it. I mean, we know what's going on. So we're going to start low, finish high, and that's going to be like that part right there.
And it tells us that this is a minimum and that this is a maximum.
So here's the deal. Halfway between those 2 points is how far we've moved up our sine curve.
Right here, halfway?
Halfway.
So
Halfway
at
between
16?
Yes.
and then halfway between a height of 5 and a height of 25.
Yes.
Those are 20 apart.
So 10.
So this is 10 right here.
So when we
that's our
go up
amplitude.
10 from 5, so 15. We're moving our whole equation up 15 units.
Yes, we are. So we're moving it up 15. So that's a vertical shift. So our D is 15.
Yes.
We've got an amplitude, which is A, of 10. What else do we have?
We've got a
B
phase
and C.
shift that moves from 0
We move from 0
to
over 16,
16.
because we're talking about sine, and we're going to write it as a positive sign. So we need
Right.
to know where is it in the middle. It's not
Right.
at 0 this time. Where is it in the middle and then going up? So we
Right.
went right 16. So that means that C is negative 16.
Right.
The period.
The period, well, we've got half of it right here.
And that took us 32 to get half.
And it took us 32 to get half, so
64 should be a whole.
So 64 should be a whole. So
So
the period, remember the formula is
2 pi over b
has
equals,
to equal 64. It has to. We don't have a choice.
and so we can do a little cross multiplication kind of thing.
Only because there's an equal sign in there. Math mistake number 1 for pre-calc kids and
I
higher
think you've
kids.
used number 1.
Well, math mistake number 1B. You can't just cross multiply everywhere when you want to.
Yeah.
You can only cross
Only certain
multiply
times.
over an equal sign.
So we could simplify 2 over 64 and make this be pi over 32.
That sounds great.
And let's write out our sinusoid now. We've got y equals a sine b.
And we saw in the previous example we need to open up parentheses.
Open a parentheses.
Come on over, Mr. Kane. We're wrapping up this problem.
Yeah, we're recording right now, Mr. Kane, but you can say hi to all the chillins, or you can choose not to.
Not to is a good choice.
They
Okay.
just heard that, so
Okay.
now you've offended them.
No, it's okay. Okay, so that's it.
That's it right there.
Let's
Now,
leave
if you
it-
want to send the pi over 32 through, you certainly may.
But you can leave it like
You
this.
can leave it like that because that's how we know what that means.
I know what that means.
I know what that
you know
means,
what that
too.
means. Everyone knows what that means.
Yeah.
So
All right, good talk. Good talk.